Hi, myself Dr. S.K. Bushra, former HOD, Department of Physics, Cotton University. The subject is physics. The topic is electrostatics. Chapter 1, Lesson 2, Conductors and Insulators. In this lesson, we'll discuss the following: conductors and insulators, electrostatic induction, and finally, charging of material bodies by electrostatic induction. The first topic is conductors and insulators. Insulators are also referred to as non-conductors and also referred to as dielectrics. We have already learned that electrostatics deals with electric charges at rest. Similarly, current electricity deals with electric charges in collective motion, which we call an electric current. Electric currents can flow across solids, liquids, and gases. At present, however, we'll limit our attention to electric currents in solids. On the basis of their ability to support electric currents, solids are classified into two categories. Conductors. Electric currents can flow in them. Metals, human and animal bodies, and the earth are examples of conductors. Insulators or non-conductors. Electric currents cannot flow in them. Most of the non-metals like wood, plastic, glass, nylon, rubber, etc. are insulators. Information, slide 1. The difference between a good conductor and a good insulator is perhaps the widest of any common physical property of solids. The electrical resistivity of a pure metal may be as low as 10 to the power minus 10 ohm centimeter at a temperature of 1 Kelvin. Electrical resistivity measures a material's opposition to an electric current. The resistivity of a good insulator may be as high as 10 to the power 22 ohm centimeter. The gap is enormous. The order is 10 to the power 32. Information, slide 2. In between the conductors and insulators, there is another class of solids called semiconductors. Semiconductors are pronounced as semiconductors as well. Semiconductors have resistivity in the range of 10 to the power minus 4 ohm centimeter if the sample is heavily doped, to 10 to the power 3 ohm centimeter if the sample is in intrinsic state. Conduction in a semiconductor is different from that in a conductor. We'll discuss about semiconductors in a subsequent lesson. Let us now conduct a question-answer session. Question: which are the charge carriers in a conductor? Answer: the electrons. Next question: do all the electrons in a conductor participate in conduction? The answer: no. Only the free electrons participate in conduction. Next question: which are the free electrons in a metal? The answer: the valence electron of the constituent atoms become the free electrons in a metal. How? To know the answer, we investigate the atomic structure of a typical metal. We pick up sodium, the simplest of them. A sodium atom has 11 electrons. The inner or core electrons, 10 in number, are very tightly bound to the parent nucleus. The outer electron, called the valence electron, is the most loosely bound. The atomic radius of sodium atom is 0.190 nanometer. In the solid state, the nearest neighbor distance in sodium is 0.371 nanometer. When an atom combines with others to form a solid, its electrons become perturbed by the presence of neighboring atoms. The perturbation is most striking for the loosely bound valence electrons. They are pulled away from the parent atoms and they find themselves in no man's land in between atoms. These electrons do not belong to any particular atom and they are free to conduct. The core electrons, on the other hand, can withstand this perturbation and remain bound to the parent atom. Hence, they are not available for conduction. Information, slide 3. A little amount of sodium, say 23 grams, have of the order of 10 to the power 23 atoms. Each atom contributes 1 electron for conduction. So for all practical purposes, we may say that a sample of sodium possesses infinite number of free electrons. Here we have used Avogadro's hypothesis. The last question, what about the protons? Protons do not contribute to the conduction process. They are tightly bound within the nucleus and are not removable from there by ordinary means. Let us now come to the second part of the lesson, electrostatic induction. First, the definition. The temporary separation of positive and negative charges in a body in presence of a charged object is called electrostatic induction. It has been observed that electrostatic induction takes place in conductors as well as in insulators. The induced negative and positive charges are always equal in magnitude. The electrostatic induction in a conductor is a manifestation of attraction among unlike charges and repulsion among like charges. Opposite charges come nearest to the inducing charges, while similar charges move to the far end. In a conductor, the induced opposite charges remain bound to the inducing charges, while the induced similar charges become the free charges, and if given a pathway, they will leave the host. The electrostatic induction, on the other hand, in an insulator is a complicated process, different from than in a conductor. We'll discuss it in a while. Induction disappears as soon as the inducing charges are removed in conductors as well as in insulators. Let us illustrate the electrostatic induction in a conductor in presence of a positive body. Bring a positively charged body near an insulated conductor. Electrostatic induction takes place with the induced unlike charges nearer to the inducing charges. Now consider electrostatic induction in a conductor in presence of a negative body. Bring a negatively charged body near an insulated conductor. Electrostatic induction takes place with the induced unlike charges nearer to the inducing charges. Information, slide 4. We know that only the free electrons are mobile in a conductor. In electrostatics, however, it is all right to describe an event in terms of apparent motion of positive charges. In figure 1, in reality, electrons have been moving to the left, leaving behind a positive ambience in the right. But it is all right to say that positive charges have moved to the right, while some negative charges have moved to the left. The events shown in the figure 2 can also be described in a similar way. Now the important question is, how does electrostatic induction occur in insulators where all charges are immobile? All charges in insulators, they are also called dielectrics, as I have mentioned earlier, are attached to the specific atoms and molecules. They are unable to participate in buck motion. Atoms and molecules of some insulators are natural dipoles, that is polar molecules, while in some others, external electric influence produces induced dipoles. As the name suggests, an electric dipole is an entity consisting of two equal and opposite charges, that is poles, separated by a distance of the order of atomic or molecular dimension. Dipoles are habitually randomly oriented in insulators. Observe the figure below. However, in presence of a charged object, the dipoles get aligned. The alignment of dipoles is caused by torques applied on them by charging body. The torques rotates the dipoles into alignment with the unlike charges of the dipoles nearer to the charging body. We'll revisit the dipoles in a later lesson. In the aligned condition of the dipoles, the intermediate layers of charges in the dielectric cancel one another, like this. The charges at the boundaries, however, remain unneutralized, producing induction in the bubbling. Let us now come to the third part of the lesson, charging of conductors by induction. Bring a charged body near an insulated conductor. Here a negatively charged body has been brought. Electrostatic induction takes place in the conductor. In presence of the charged body, connect the conductor to the ground with a conducting wire. The repulsion of the charged body urges the free charges, negative here, in the conductor to move to the ground. The ground readily accepts all free charges, as always, in a limitless manner. However, the attraction of the charged body prevents the bound charges, positive here, in the conductor from escaping. Disconnect the conductor from the ground in presence of the charged body. Remove the charged body. The charges in the conductor distribute on its surface as per certain rules. We will discuss these rules in the next lesson. If we had used a positive body for charging, the conductor would have been charged negatively. Insulators cannot be charged by induction. We have seen that induced charges are actually part of tiny dipoles. They are bound and can never be transferred to the ground. And we know that if one type of charge are not removed, the body will not get charged. Once the inducing body is removed from the scene, the dipoles of the insulator immediately get randomized and the induction disappears. We have come to the end of the lesson 2. In the next lesson, we'll discuss charging of materials by bodies, charging of material bodies by conduction, distribution of charges in a conductor, and some interesting electrostatic experiments. Thank you.